Today we're going to look about solubility and today we're going to take a look at solubility and the solution process. A lot of you know how you dissolve something, and so dissolving a solid in a liquid is a dynamic process. And so what that means is that whatever that you have gets dissolved always gets reformed in the solute in the solvent. But what we see is we with our own eyes, we don't see the change. But what happens is the rate of dissolution or dissolving equals the rate of solution. So what happens is whatever goes into solution will come out of solution at the same rate until some sort of equilibrium will be reached. Time for a demo. Here I have a glass of water, and here I have some brown sugar. So what we're going to do is we're going to make a solution of brown sugar water. Fancy. All right, so what we'll do is we have the solvent, and then here we have the solute. So what we're going to do is we're going to put this together, and we're going to mix it up. Now I'm going to speed up the process, and when we get to kinetics in chapter 12 next semester, we'll take a look and see ways that we can speed up a chemical reaction or a process like this happening. So one way is stirring. Another way is heating it up, which I don't have downstairs in my room here. And then we also have we had a high surface area, and then I don't need a catalyst here. So if we take a look here, we have, you can kind of see this is a little brown. This is brown sugar water, and so it's brown. You can trust me, it's brown. Okay. Oh, there. That looks a little better. Now, what happened on a molecular level? Let's take a look at it now. So what we're going to do is we're going to take a look at the molecules. So if we have the water molecules and we have the brown sugar molecules, so I'll put the sugar here, and then we'll put the water here. Okay, so in the process of forming a liquid solution, there are 3 steps. And then the first step is expanding the solute. So what gets dissolved? So expanding the solute. Now think about, in order to expand the solute, does energy need to be added into the system or taken out? We'll check that at the end. Then the second step in the formation of a liquid solution is expanding the solvent. So think about it once again. Would the delta H of this process, step 2, be positive or negative? Would you need to add energy into the system or take energy out of the system? And then number 3, in order to put it all together, is to form the solution by putting them all together. And when I mean expanding water, let's make this solvent. So in this case, it's the water. And then expanding the solute, in this case, it's the sugar. All right, so what does it look like? Well, here, on a molecular level, expanding the solute. So if we had these particles, and the sugar particles were like, the sugar molecules were like this, expanding it would look like something to this degree. So we make room for the solute and the solvent particles to fit into each other. All right, so that's step 1, expanding the solute. So would the delta H be positive or would it be negative? Okay, well here, let's take a look. So expanding the solute would mean that we would need to make space in between. We need to make the particles farther away from each other. So we need to have a delta H that's positive here. Now, if we take a look with the water, we'll take these molecules, put them there. Now, I understand that these are not oriented like, like whether you have H2O with the hydrogen bonding. I just put it a little rudimentary drawing where you have the intermolecular forces in between. So we make space, and then we'll have something to this degree. So in this case, then, would expanding the solvent, would it be a positive or negative delta H for this? Well, if you guessed that it was a positive delta H for this process, this step, then that's correct. Now, what we're going to do is we're going to form the solution. Now, to form the solution, we're going to combine the solute and the solvent together. We're going to put them together, and then we're going to contract it. And in the process of doing so, we should take out energy, or energy should be released from here. So now, like magic, 1, 2, and 3. The particles got mixed together, and then what we would see is that they would actually go closer together, and then you would end up with your brown sugar water. Ah, fantastic. And so what happens is when you add these 3 steps together, you get the overall enthalpy, or delta H, of the formation of the liquid solution, just like in Hess's law. So this would be the delta H of the solution, forming the solution that we have here. And they just abbreviate solution SOL with an N here. And then these 2 steps, expanding the solvent and forming the solution, this basically quantifies the enthalpy of hydration. So just like how it sounds, involving the solvent, involving water, and then making the solution. So hopefully this helps you out with the formation of this liquid solution. Let's go back to the regularly scheduled video. Now, in terms of solubility, like dissolves like is kind of like the 3 words for describing how solutes and solvents dissolve. So if their intermolecular forces are similar, that means that 2 substances, when you mix them, they would be miscible, which means that they are mixable. M-I-S-C-I-B-L-E, miscible. Now, if they're not mixable, they're immiscible. And I'll type in the words down on the bottom just so you can kind of see the difference. All right, so if we take a look here, nonpolar molecules are soluble in nonpolar solvents. So like dissolves like. So nonpolar molecules are soluble in nonpolar solvents. And so like carbon tetrachloride is a nonpolar molecule, and it would be soluble in benzene, which is also a nonpolar molecule. And then polar molecules are soluble in polar solvents. So if we had ethanol, ethanol has a hydroxide over here, or a hydroxyl group. And so that makes hydrogen bonding. So ethanol could be soluble in water. Now, it does have some nonpolar components, but it does have one hydrogen bond that it's able to make. So it can be dissolved there. And then ionic compounds are more soluble in polar solvents. So like say if we had salt in water, the cation, or the Na plus, would attract to the negative oxygen in the water, and then, or the hydroxide, and then the chloride ion from the NaCl would be attracted to the positive hydrogen that we have over here. So ionic compounds would be soluble in polar solvents. So some common sense here: solid, solubility, and temperature. So if you ever tried to make Jello, it tells you that you need to heat up the water in a saucepan on your stove. And then when you put the Jello powder, or basically sugar with the coloring in it, what happens is it dissolves pretty quickly. So in general, most substances will increase their solubility when you increase the temperature. So if we dissolve a solid, then what we're doing is, by increasing the temperature, we're increasing the average kinetic energy of the particles. So we're expanding them, and we allow the solid to fill in the spaces in between the expanded solvent. And so in general, they increase. There are a few exceptions, but you don't have to worry about that. So in general, solubility increases with increasing temperature. So this is for a solid solute in a liquid solvent. And then gas. So think about gas solubility and temperature. Think about soda. Soda in a can is under high pressure. And usually when you buy it at the store, it's usually on the shelf. But if you go to 7-Eleven, or you go to one of those convenience stores, usually it's cold. And so what happens is, if we take a look at the graph, the solubility of a gas would decrease as you increase the temperature. And it should make sense also, because as we increase the temperature, we're increasing the average kinetic energy of the particles. And so the gas would have the tendency to escape out of the liquid solvent. And so solubility of gas usually decreases with increasing temperature. And that should make sense based on what we learned about gas laws. And then Henry's law is the other piece. The reason why your soda is under a high pressure is because of this. If we take a look here on the left, we have low pressure over our liquid. and we have a low concentration of gas inside. But what happens on the right side is like in your soda can, we have a high pressure, which is basically your soda can is pressurized, and then we have a high concentration of gas inside, which is the carbon dioxide or the carbonated water that you have there. You have a high concentration of carbon dioxide in the soda. And so that's what happens. And when you open it, when you open the can, what happens is then you end up with, if you leave it out, the pressure over the gas is low. And so then you would have a low concentration of carbon dioxide and your soda goes flat. And this is because of Henry's law. So the solubility of a gas in a liquid is directly proportional to the pressure of the gas over the solution. And so that's basically it with a soda can. And then for tomorrow, we'll go over some units of concentration. So we'll go over mole fraction, which is just like it says on the right, basically the moles of the component that you're looking at divided by the total moles. And then the mass percent is similar, where you have the mass of the solute or the component you're looking at divided by the total mass of the solution, and then you multiply it times 100 because it's mass percent, so 100%. And then other units that you'll probably see, especially in APES class, AP Environmental Sciences, is like parts per million, which is the mass of solute divided by the mass of the solution times a million. And then parts per billion, which is even smaller, which is the same formula, except instead of times a million, it'll be times a billion, times 10 to the ninth. And so we'll check those out tomorrow, the units of concentration, and do a few calculations for practice.